Hello, this is Steve Stannard, and this is Introduction to Lighting. Have you ever wondered what light is? When you've been in the lighting industry as long as I have, you spend a lot of time actually wondering about this. But for most of us, because it's so natural for us, we don't even think about what is light and how we see. Light is a form of what we call electromagnetic radiation. We're actually familiar with in many different forms. Sometimes we refer to it as a wave propagating through space, and sometimes we refer to it as a particle. Does anybody know what a particle of electromagnetic radiation or particle of light is called? It's called a photon, right? So those of you who are Trekkies know about photon torpedoes, right? This is old hat. Okay, but photons is the same thing. It's a particle of light rather than a wave of light. When we talk about waves, we often refer to wavelength. Wavelength is the distance from the peak of one wave to the peak of the next wave. And we described different forms of electromagnetic radiation by their wavelengths. All right? Wavelengths can come in different sizes, if you will. Larger ones can be as big as a football field. Right? So they can be extremely long wavelengths. And these are the wavelengths that we encounter when we deal with radio. Right? So if you listen to radio on your way into work, if you're not listening to digital radio, you're listening to AM or FM radio. That's a long wavelength signal. Right? As the wavelengths get shorter, okay, we get into an area that we call microwaves. And microwaves are a wavelength that's about roughly an inch long. Right? So in that dimension, we use microwaves for what? We use it for cooking, right? We have microwave ovens. We use it for telecommunications, also for radar, right? So we have a lot of different applications for microwaves. As the wavelengths get shorter still, we get into an area that we call infrared. We're familiar with as radiant heat, right? So when you feel the heat coming off of something, you're feeling electromagnetic radiation of a wavelength in the infrared band. When the wavelengths get shorter than that, we get into a very narrow area that we see as visible light. We'll come back to that in a second. When we get beyond visible light, we get into a ultraviolet area. Okay, ultraviolet does what for us? Okay, ultraviolet gives us a sunburn, right, or a tan, right? So it's actually radiation burns from ultraviolet radiation. Ultraviolet is also germicidal. It'll kill germs, or it'll kill bacteria. So it's often used in the medical industry to sterilize things. When we get beyond ultraviolet, we get into the X-ray band. X-rays have high enough energy that they actually penetrate living tissues, and so we use those, of course, for medical imaging. We use X-rays all the time. Beyond X-rays, we get into gamma rays, which are very, very high energy waves that are basically dangerous to any life form. And these are the results of nuclear exchanges. We try not to deal with gamma rays when we can. The visible portion of the spectrum, right, the part that we can actually see with our eyes, if we were to lay that whole spectrum out, okay, from all the AM, FM radio waves all the way up to gamma rays, if we were to lay that out between here and New York, for example, about 2,500 miles, the visible portion would only be about an inch. Right? So this incredibly tiny little band, this very narrow band, is what we can perceive with our eyes. Right? And we perceive different wavelengths within that band as different colors. So that's how we distinguish color. This is a graph that was generated by studying college students because they're basically very cheap to experiment with. And they measured the sensitivity of people's eyes to different wavelengths. And we discovered that in a spectrum from about 400 to 700 nanometers, and a nanometer is a 10 to the minus ninth meters, very, very tiny dimension. Okay, we have a changing sensitivity to light, right? So in around 400 nanometers, which is the violet, blue-violet end of the spectrum, we have very low sensitivity. But as we move across the spectrum into the blues, and then finally the green and yellow-green is where our sensitivity peaks, which is about 550 nanometers. And then as we continue to move up the spectrum, we get into the yellow, orange, and then red portion of the spectrum, about 700 nanometers. This we call the V lambda curve. That upside down Y is the Greek letter lambda, and that means whenever you see a lambda, it means we're referring to wavelength. The V, of course, stands for visibility. Right? Now, the reason that this is important is that if you're going to create a new light source, if you're going to create a new light bulb, you want that to convert its electrical energy to electromagnetic radiation within this visible spectrum from 400 to 700 nanometers. Because if it creates output, if it creates energy outside the visible spectrum, it's wasted. This is the classic case of this is the incandescent light bulbs. Incandescent lamps, okay, put out very little blue, but their output increases as we move across the spectrum toward the red. And unfortunately, the output continues to increase after we leave the visible spectrum and get into the infrared part of the spectrum. In fact, only about 10% of the energy from an incandescent lamp is in the visible spectrum, 90% is in the infrared, which makes incandescent lamps a much more efficient heat source than they are a light source. Right? So again, if you're going to create a new light source or a new lamp, you want it to focus all of its output in that visible part of the spectrum.